Chapter 1, Lecture 2. So let's talk a little bit about viscosity. One of the reasons liquids and gases are classified as fluids is because they continually deform when they flow. What happens is that this figure 110 is kind of exaggerated. The depth is kind of exaggerated. But here you have a stationary plate, and on the top you have a moving plate, and between them you have a fluid. So when let's apply a small force to the top plate, and the top plate will move to the right. So u here is the velocity of the top plate. But if you look macroscopically at the levels, you have this kind of shearing effect where closest to the stationary plate, it's harder to move, so it doesn't move very much. And then as you get farther toward the top plate that's moving, the shear becomes greater. So it's kind of a tearing effect. You can't see this from with your naked eye, but macroscopically you can. This resistance of the fluid to flow is what's called viscosity. The higher the viscosity, the more difficult it is to move through the fluid. So, for example, for like water or oil, it's going to be different for each one of those kinds of fluids. So our book defines what's known as the dynamic viscosity. This is the resistance to shearing flows. So again, here we have two plates. Uh, Capital U is the velocity of the top plate. The bottom plate is stationary. And so here you can see that shearing effect is going to cause the fluids to move at different levels as you go from the bottom to the top of the plate. So the velocity is not the same here. It's going to be at this part of the fluid, the velocity is going to be higher moving to the right than it is closer to the bottom plate. So the magnitude of the force required to move the top plate is found to be proportional to several things. First, it's proportional to the density of the fluid, which is the mu. It's proportional to the area of the plate you're moving, and it's proportional to this ratio of u, which is the velocity compared to the depth of the fluid. So if you take, for example, this is the average, so like the magnitude of the force. If you look at the force divided by the area, so you divide both sides of this equation by the area, you have F over A, which is the torque. It's the force per unit area. So that's F over A, which is the torque. What you're left with is this mu factor, which is the density. And so this here is like U over Y. This is U is the velocity, Y is the depth, and so this is kind of like an average. But if you look at it from at a specific point, you can replace the delta U and delta Y by differential du dy. So d du is sort of like the slope of the velocity compared to the depth of the fluid. This was discovered by Isaac Newton way back in the 17th century, and it's what's referred to as Newton's law of viscosity. So du over dy is kind of like the gradient. Tau is the torque, and mu is the density of the fluid. So let's take a look at this Newton's law of viscosity. So for different fluids, you can see here, this is plotted. You plot the torque on the vertical axis compared to the gradient, this du dy. And so the slope of this curve is simply going to be the viscosity. So you can see for air all the way up to crude oil, the higher the slope, the higher the density of the fluid, and also the more harder it is to flow, right? So air is pretty easy to get to move, but crude oil is pretty dense, so it's very hard to cause it to flow. So, a curve that follows Newton's law of viscosity is what's called a Newtonian fluid, but if it doesn't follow that, it's referred to as a non-Newtonian fluid. So you have two cases where it either bends up this way or it bends over this way. So this might remind you of, for example, like Hooke's law, right? Hooke's law, we call it a law, but it's not really a law because Hooke's law is only valid over a certain region. Uh, for example, like a slinky. A slinky, you can stretch and it'll go back to its original form, but if you stretch it too far, it won't return to its original form. So here, even for this, for example, pseudoplastic fluid, if you limit the case where it's between like here and there, it's sort of linear, but it's almost like piecewise linear, right? It's sort of straight over a certain section, but overall it kind of bends, where a true Newtonian fluid is strictly a straight line. The viscosity is also affected by the pressure and temperature. Obviously, on a very cold morning, you find that motor oil doesn't flow as well as it does in the hot summertime. So if you plot a graph of the viscosity versus the temperature, you see you have different curves for different fluids. You can see for gases, it's sort of as the temperature increases, the viscosity increases. Kind of interesting, right? Whereas for fluids, it's exactly the kind of reverse. These kind of curves, you can fit this viscosity curves to two equations, and so our book talks about, there's an equation for liquid, and there's an equation for gases. These have specific names. Andre's equation and Sutherland's equation are the two equations that oftentimes people work with. In these equations, of course, the capital B and C are simply constants that you use to fit the curve, and temperature is the T is the temperature in Kelvin. So another way to express the fluid viscosity of a fluid is to represent it by what's known as this kinematic viscosity. This is a symbol. It looks like a V, but it's a nu. And this is related to the density and to the viscosity. So remember, this mu is the dynamic viscosity, and rho is the density. So for different fluids, our book gives these to us. For example, here's for water. This is back in table Appendix A. It plots all of these quantities versus the temperature. So you can see here at 20 degrees C, it gives you the density, the dynamic viscosity, and the kinematic viscosity, and also the vapor pressure at those different levels. This other curve this other table is for different liquids. So he gives a table for water at all kinds of temperatures, and he also gives for different liquids at all at standard atmospheric pressure and temperature. So how do you measure viscosity? Well, the common way you measure it is to use what's called a Brookfield viscosometer. And so basically what this device is, you can look online. There's several good YouTube videos of the Brookfield viscosometer. It's basically, you have a cylinder within a cylinder, and so here the blue is your liquid you pump in here. So this one's this outer one's a fixed cylinder, and so you basically spin this thing. This is a rotating container, and you measure the how much twist the inner cylinder is caused. So if you have a very dense fluid in here, it's very hard to turn this. But if you have a very low viscosity, low density fluid, it's very easy to turn this. So by measuring this twist of this wire, this torque can be calculated. And if you take mechanics and materials, you might actually even look at how to calculate this. Our book doesn't actually do this. It just gives us the formula for this. And so here, omega is the rotation rate, and has the inner and outer radiuses of the cylinders, and h is the height of the fluid. M is actually the measured torque, and T is the thickness between the inner and outer cylinders. So it's very easy to calculate these, and honestly, it's Most of the meters have gauges that you can just read what it is. You don't really have to do any math on it or anything to actually calculate this. So let's take a look at example 1.5 in our textbook. Here he shows a plate that rests on top of a thin film of water. Uh, it's at a temperature of 25 degrees C. If a pressure difference occurs between A and B, and a small force is exerted on the top plate, the velocity profile across the in between the two plates can be described as a simple formula. And he just gives this to us, this formula. He says y is in meters. Remember, y is the distance between the plate. He wants us to determine the shear stress acting on the fixed surface and on the bottom of the plate. So here we're going to use the Newton's law of viscosity. We have u as a function of y, so we can take this derivative and we can just plug in the numbers. It's pretty easy to calculate here. So again, first of all, we can find what the viscosity of water is at 25 degrees C using those tables. If you look it up, it's 0.897 times 10 to the minus 3 Newton seconds per square meter. We can calculate the gradient, so it's du dy, and we know what u is as a function of y, so we can calculate this derivative. So the derivative of 40y is just 40. The derivative of 800y squared is, the 2 comes down, 2 times 800 is 1600 y. And so therefore, we can calculate the gradient at any height we want, any value of y. So certainly at y equals 0, that's at the fixed surface. You can plug this in. 1600 times y is 0. You got the mu here is which we calculated up here. So we can find the torque is 35.88 times 10 to the minus 3 newtons per square meter. And that's 35.9 millipascals. At the bottom of the plate, which is at 10 millimeters, so that's, again, we can plug in the gradient. So it's 40 minus 1600 times 0.01, that's the 10 millimeters. Calculate this out and you get 21.5 millipascals. So you can see it has a different, a tau value at the bottom and the top of the plate. So he concludes by saying, that the larger shear stress develops on the fixed plate surface rather than at the bottom of the plate, since the velocity gradient is higher up at the top of the plate, which makes perfect sense. So let's look at example 1.6. This is another great example that he works. He has a 100 kilogram plate shown here, resting on a very thin film of 10W30 oil. You can look up the viscosity of the oil. It's in the appendix A again. It's 0.0652 Newton second per square meters. He wants us to find the force P that must be applied to the center of the plate to slide over the oil with a constant velocity of 0.2 meters per second. Assume the oil thickness is 0.1 millimeters and the velocity profile across the plate, this thickness is linear. The bottom of the plate has a contact area of 0.75 square meters with the oil. So here, again, we're going to treat this as a Newtonian fluid. That's the way we're going to treat all of our fluids in this course. So first thing we can do is we can draw a feed body diagram of the plate. We also have the weight pushing down on it. It's 100 times G. Again, these are in metric units. So 100 kilograms times G, that's the downward force. The upward force is the normal force of the bottom pushing up on the top. P is the applied force at 30 degree angle. So if you sum forces in the horizontal direction, those are going to add to 0 because we want it to slide with a constant velocity, right? So if the velocity is constant, the acceleration is going to be 0. So F equals ma. Well, the A part is 0. This is just a statics problem, basically, right? So what forces are in the horizontal direction? You have F And you have the component of P in the horizontal direction, which would be P times cosine 30. So here you can calculate F is equal to 0.866, which is the cosine of 30 times P. We can calculate the stress on the plate. That's the force divided by the area. So here's our force divided by the area. We're told that at the bottom is 0.75. That's the contact area. So the stress is going to be 1.155 times P. Now, how do we go further? Well, using Newton's law of viscosity, we're told that the velocity profile is constant. So here, du dy. Well, the top velocity he tells us is 0.2 meters per second, and the bottom that's just the thickness, right? So here we're going to replace this derivative by like this average values, right? So instead of du dy, we're going to use delta u delta t. Well, delta u is the velocity, 0 down here and its maximum up here. So the delta u is 0.2 meters per second. The thickness is this 0.1 millimeter. So the stress we calculated on the previous slide, mu, we know what that is. We looked that up, and so u over t, we plug that in. So the only unknown we don't know is p. So you can work through this, divide both sides of the equation by the 1.155, and so you calculate p as 113 newtons. All right, so that's the end of chapter 1 lectures. Again, this chapter basically just sets out some basic properties. I'll assign some homework problems to take a look at and give you a few hints on how to get started on them. All right, until next time.